So good morning. So we'll study today an important topic and an easy topic. It's called self-inductance and mutual inductance. So what is self-induction? I have told you in passing in the last class. Self-induction is a current carrying conductor has an associated magnetic field around it. If you try to increase the current through the coil, the flux linkage of the coil also increases. This increasing flux induces an EMF in the conductor that opposes the growth of the current. Yesterday, Bhadra explained this very clearly. So there is a coil, and if you try to increase the current, the flux will be produced. So this increasing flux will induce an EMF. What will that do? This increases because of increasing fluxes because of the increasing current. So the EMF will be opposing this increase. Similarly, if you try to decrease the current in the coil, then the decreasing flux linkage induces an EMF that opposes the decay of the current. So here, you can see here, this is a coil, and when I increase the current IFT, what happens? Phi FT will increase. So when phi FT increases, what happens? An EMF will be induced which will oppose the increase in current. So that is what is self-induction. In both cases, the energy stored in the magnetic field gives rise to the induced current. Thus, a coil or circuit possesses a property called self-inductance by which it opposes both growth and decay of current in it. So in short, what is self-inductance? Self-inductance is a property of the coil which will oppose the increase in current as well as decay of current. If the current is increasing, it will oppose the increase of current. If the current is decaying, it will oppose the decay of current. The proportionality constant L is called self-inductance or coefficient of self-induction. But the proportionality constant is called self-inductance or coefficient of self-induction. And unit of self-inductance is Henry. So what did we learn? A coil has a property which will oppose the growth and decay of the current. This property is called self-inductance. So let us look at some equations. So we know that the flux linkage is proportional to the current. When we from our basic knowledge, we know that when the current increases, you look at this coil, when the current increases, flux will increase. So what can I write? And what is flux linkage? N phi. N phi will increase when current increases. So I can write N phi is proportional to I, or I can write N phi is equal to L into I. I can write N phi is equal to L into I. So let us derive an expression for self-inductance. So to derive self-inductance, let us consider this coil. We are going to derive an expression for self-inductance. Consider this coil. You can see this coil.
Yes, sir.
Yes, sir. Can you see this coil? It has N turns. So what is the flux is phi, and what is the flux linkage? Flux linkage is N phi, and N phi is equal to BAN. Why BAN? Phi is B into A. Therefore, N phi is N into BA, or it is BAN. So you have that figure in your mind. So consider a long solenoid of length L. Total number of turns N, area is A, I be the current. Then we know that magnetic flux through single coil is B into A, and magnetic flux through the solenoid of N turns is BAN. N phi is BAN. And what is B? You know that B is equal to mu 0 into H if it is R coil, R core. And what is H? We have studied in the last class. H is the magnetic field intensity, and H is equal to Ni by L. So I have this is what Ni by L is B into mu, Ni by L is H into mu 0 is B. That into An is our N phi, mu 0 N square Ai by L. And we know that N phi is equal to what? Harinandan, N phi is equal to?
N phi is equal to flux link is Li.
So if I equate that, N phi equal to Li, N phi is equal to Li, N phi is equal to mu 0 N square Ai by L. What are we trying to do? We want to get an expression for self-inductance. So if you look at these two equations, what is L, Harinandan? N phi is equal to Li, N phi is equal to mu 0 N square Ai by L. Comparing these two equations, what is L?
Sir, yes, sir, N square. Sir, L is equal to mu 0 N square A by L.
Very good. It is mu 0 N square A by L. So that is the derivation. We get the expression for self-inductance of an air-cooled solenoid. So we have an expression for self-inductance. Self-inductance is a property of the coil. I asked you in the series about self-inductance because I want you to think about self-inductance. And you know about something about self-inductance in school. So it is mu 0 N square A by L. If it is air-cooled, suppose there's iron in it. Usually, I told you about transformer. Transformer has some iron core in it. An electromagnet has an iron core in it. Tube. You have seen tube, isn't it? You have seen the tube light. Now it is electronic tube. Old tubes have a chalk. And inside the chalk, there is a solenoid. And everywhere inside, it's not air-cooled. It will have some core. So if the core is having a permeability mu r, then L is equal to mu 0 mu r N square A by L. What is the relationship between B and H in general? B for air core, it is in air, B is equal to mu 0 H. In a medium, what is B? In some medium, what is B?
Sir, B is equal to mu H.
Mu H, and mu is equal to?
Mu 0 mu R.
Mu 0 mu R. Very good, very good. So we got the expression for L. So let us see how Harinandan explains this. So we have seen expression for self-inductance. Let us see the direction of self-induced EMF. So I have to rub this. So according to Lenz's law, according to Faraday's law of electromagnetic induction, the induced EMF is directly proportional to the rate of change of flux linkage. Also, the direction of the induced EMF can be found out by Lenz's law. E is equal to minus N d phi by dt, isn't it? We know that E, magnitude of E is N d phi by dt, and we know that N phi is equal to Li. Therefore, what is E? E is equal to minus d by dt of Li. L is a constant. Therefore, what can I say? I can write E as minus L di by dt. Suppose di by dt is 1 ampere per second, then L is equal to E. So to find self-inductance, what you can do is, you find the EMF induced when there is a rate of change of current is 1 ampere. So I'll read this. Hence, the coefficient of self-inductance may be defined as the amount of EMF induced in the coil when the current changes at a rate of 1 ampere per second. Is that okay, Nandini? And if you have many inductance in series, then effective inductance, if the mutual inductance is negligible, the effective inductance is L1 plus L2. If you have in parallel, it is 1 by L is equal to 1 by L1 plus 1 by L2. So two inductance in series, L1 plus L2. Two in parallel, 1 by L is equal to 1 by L1 plus 1 by L2. If mutual inductance is negligible, we'll be seeing mutual inductance shortly. Over to you, Nandini. Please explain this 2 slides. Yes, Nandini. Nandana Rani from Anjalamud, Neeravil. Nandana ille. Can you hear me, Harinandan?
Yes, sir, I can hear you.
What happened to Nandana Rani?
Sir, I don't know.
Who is number 22? Harinandan, who is number 22?
Sir, it's Deepika.
Deepika, can you mutual inductance? Mutual induction. Okay. So consider these 2 coils. Okay, you have coil 1 here, coil 2 here. Suppose current in this coil changes. Suppose there's a current in this coil, say I amperes. What happens? There's a flux. There's a lot of flux linking the coil 1, and half of the flux is linking coil 2 also. So you have a coil, you have 2 coils, and current is there in 1 coil. Because of this current in 1 coil, what happens? There's a flux linkage with coil 1, but there is also a flux linkage with coil 2. And if the flux in this coil 1 changes, flux linking the coil 2 also will change. And this change will induce an EMF here in coil 2. So what is the magic? The flux change in coil 1 will induce an EMF in coil 2. So that induction is called mutual induction. Obviously, due to self-induction, an EMF will be induced in the coil 1. Also, the time varying magnetic field is linked with coil 2, as I told you. Then coil 1 and coil 2 are magnetic coupled. Thus, the varying field in coil 1 induces an EMF in coil 2. I'll repeat again. You have 2 coils. In coil 1, there's a current. If there's a current in coil 1, there will be a flux in coil 1, and there will be a flux linkage in coil 2 also. If the current in coil 1 changes, the flux linking coil 1 will change. Similarly, the flux linking in coil 2 also will change. And this change in flux linking in coil 2 will produce an EMF. And this EMF is called mutually induced EMF. Similarly, if a varying current flows through coil 2, an EMF will be induced in coil 1. That is, this phenomena is mutual. Thus, the phenomena of induction of EMF in one circuit or coil due to the variation of current in the neighboring coil is called mutual induction. The amount of EMF induced by mutual inductance depends on the number of turns of the individual coils, relative distance, orientation, current through coils. The direction of the induced EMF is given by Lenz's law. Let me explain again qualitatively. Say here, there is N1 turns is there, N2 turns is there. What we have studied the last 5 minutes is when current changes in coil 1, there will be a flux linking in coil 1, and that flux linking in coil 1 will change. Not only that, since it is linking coil 2, the flux linking coil 2 also will change. So whenever the flux linking in coil 2 changes, an EMF will be induced here. This EMF is called mutually induced EMF. Yes, Nandana, are your mic okay? Nandana Rani. Okay,
sir. Mutual induction. Consider a time varying current flowing through a coil as shown in the figure 1. This leads to the varying magnetic field around the coil. Obviously, due to self-induction, an EMF will be induced in the coil 1. Also, the time varying magnetic field is linked with the coil 2. Then coil 1 and 2 are magnetically coupled. Thus, the varying magnetic field of coil 1 induces an EMF in coil 2. Okay, Anna sir.
Yes, good. ഇതും കൂടെ പറഞ്ഞോളൂ. Yes.
Here, an EMF is induced in coil 2 due to the variation of current in the coil 1. Similarly, if a varying current flows through the coil 2, an EMF will be induced in 1. That is the phenomenon of mutual induction. Induction is mutual. The phenomenon, thus the phenomenon of induction of EMF in one circuit or coil due to the variation of current in a neighboring circuit is called a mutual induction. The amount of EMF induced by mutual induction depend on the the number of turns of the individual coil, 2, relative distance, 3, orientation, and 4, current through the coils.
Good. So let us see this. Can you see this slide, Nandana Rani?
Yes, sir.
Consider two coils coupled magnetically. Let me bring that figure here. Figure in. Okay. Yes, consider two coils coupled magnetically. So we have seen in the last slide two coils. They are coupled magnetically. Then a fraction of the flux due to one coil is linked with the other. We have seen two coils earlier, coil 1 and coil 2. So we'll say it is magnetically coupled when part of the flux is there in coil 1 is linking with coil 2. So if the two coils are close by, as shown in an earlier figure, so here we can see that half of the flux is linking coil 2. Here coil 1 and coil 2 are close. So half is linking with coil 2. Suppose it's still closer, the flux linking, the coupling will be more. If it is far away, the coupling will be less. Let us look into it. So in general, we can say a fraction of flux in one coil will link with the other coil. This fraction will be maybe 50%, maybe 100%. If you are expressing it as a fraction, it may be 0.5 the flux linking coil 2. We'll call it as phi 1 2. Maybe 0.5 into phi 1, or maybe 0.7 into phi 1, or maybe phi 1 itself. Suppose coil 1 carries a current I1, developing a magnetic flux phi 1 around the coil. As a part of phi 1, say phi 1 2 is linking, then flux linkage is N2 phi 1 2 is directly proportional to I1. That is the point here. When we are deriving expression for mutual inductance, we want the flux linkage. What is the flux linkage of coil 2 because of current in coil 1? It is N2 phi 1 2. And this N2 phi 1 2 is proportional to current I1. N2 phi 1 2 is proportional to current I1. And the proportionality constant is called the mutual inductance. So N2 phi 1 2 is equal to M12 I1. So according to Lenz's law, E is equal to minus d by dt of N2 phi 1 2. And that is equal to minus M di1 by dt. So let us derive an expression for mutual inductance. Thus, coefficient of mutual inductance may be defined as the amount of EMF induced in one coil when the current in the coil changes at a rate of 1 ampere per second. The unit, the SI unit of coefficient of mutual inductance is also Henry. So we had a formula E is equal to L di by dt. Now we have another formula E2. The EMF induced in coil 2 is equal to M into di1 by dt. So what is M? M is the mutual inductance. So what is mutual inductance? If di1 by dt is equal to 1, then E is equal to M. So the mutual inductance can be defined as the magnitude of EMF induced in coil 2 due to a change in current in coil 1 at a rate of 1 ampere per second. Let us derive an expression for mutual inductance. Consider a long solenoid of length L. the total number of turns N1. Let I be the current through the primary. Over this primary, N2 turns of secondary are wound. Consider flux through the single turn as the flux through the secondary. So this figure is what I was looking at. So let us look at here. Consider a long solenoid of length L. This is the first solenoid. The length of the solenoid is L, small l, and it contains N1 primary turns. Now we have another solenoid wound over it so that the flux linking will be more. Let it have N2 turns. Consider the flux through single turn as flux through the secondary. So what will be phi? Phi will be B into A. What will be N2 phi? N2 phi will be N2 into B into A. And what is B? As Hari Nandan has said, B is mu0 N1 I by L. Why N1? Because the flux is produced by current in coil 1. So we have N2 phi is equal to N2 into mu0 N1 I by L into A. If I rearrange the terms, I get mu0 N1 N2 AI by L. We know N2 phi is Mi. So if I compare the above two equation, N2 phi equal to Mi and N2 phi is equal to mu0 N1 N2 AI by L, I will get M as mu0 N1 N2 A by L. If the permeability is mu r, then it is mu0 mu r N square A by L. Over to you, Hari Nandana Rani. Nandana,
Sir,
please explain this. Nandana Rani, can you hear me?
yes, sir.
Yes. So consider, now let us derive another thing called coefficient of coupling. Okay. This is important for solving problems, and the idea is very simple. Consider two magnetically coupled coils, coil 1 and coil 2. Let I1 be the current through coil 1. The magnetic flux produced in coil 1 is phi1. So this is something which is there now in your mind very clearly. When there is current, there is flux. When there is current in coil 1, there is a flux in coil 1 given by phi1. A part of this flux is linked with coil 2. The fraction of magnetic flux produced by the current in one coil that links with other is known as coefficient of coupling. The extreme values of K are 1 and 0. If it is very closely coupled, then K is equal to 1. If you have one coil at Pericode and another coil at Chinnakada, then if there's a flux in coil 1, there won't be any linkage in a coil at Chinnakada. Such a case, we say the coefficient of coupling is 0. It needn't be Pericode and Chinnakada if it is far apart. If it is in one coil is in your classroom and another coil is in chemical block, then also the coefficient of coupling will be 0. So the coefficient of coupling will be between 0 and 1. Hari Nandan, is it clear the coefficient of coupling?
Yes, sir.
If K is equal to 0, then no flux of coil 1 is linked with coil 2. They are magnetically isolated. Hence, K is a measure of how much flux of one coil is coupled to the other. If we denote the flux of coil 1 linked with coil 2 by phi 1 2, then we can write K phi 1 is equal to phi 1 2. And similarly, K phi 2 is equal to phi 2 1. When coil 1 carries a current, it also develops a self-induced EMF. Yes. From the last two expressions, we got N1 phi 1 is equal to L1 I1. Therefore, what is L1? L1 is N1 phi 1 by I1. And what is L2? L2 is N2 phi 2 by I2. So what is this? N1 phi 1 is equal to L1 I1. Why? Because we have seen this expression earlier. So what is L1? L1 is N1 phi 1 by I1. What is L2? N2 phi 2 by I2. And what is MI1? It is N2 phi 1 2. And M is also equal to N2 phi 1 2 by I1. Similarly, M is N1 phi 2 1 by I2. Therefore, M square is this. N2 phi 1 2 by I1 and N1 phi 2 1 by I2. So I can rearrange the terms. I can take N1 and N2 outside. And phi 1 2, we know it is K phi 1. And phi 2 1 is K phi 2. So I got M square is equal to K square L1 L2. Harinandana, Harinandan, thank you. So we have derived a very important equation. If self-inductance of coil 1 is L1, self-inductance of coil 2 is L2, and coupling coefficient is K, then mutual inductance M is equal to K into root of L1, L2. So let us do a problem. If K is equal to 0, M is equal to 0. That is, there is no coupling. If there is perfect coupling, M is equal to root of L1, L2. This is another point which all of you should note. I told you a formula for adding inductance. If you have two inductance L1 and L2, and if there is a mutual inductance, L is not equal to L1 plus L2, it is something more. L1 plus L2 plus 2M. And sometimes it is L1 plus L2 minus 2M. So if we say if it is aiding, then if the two fluxes are aiding, then it is L1 plus L2 plus 2M. If two fluxes are opposing, it is L1 plus L2 minus 2M. So using these formulas, there are a few problems. Please read this question, Harinandan.
Yes, sir. Two coils having 150 and 200 turns respectively are wound side by side on a closed magnetic circuit of cross section 1.5 into 10 raised to minus 2 meter square and mean length 3 meter. The relative permeability of the magnetic circuit is 2000. Calculate 1. The mutual inductance between the coils. 2. Voltage induced in the second coil if the current changes from 0 to 10 ampere in the first coil in 20 meter second. Meter plus 20 meters. 20 millisecond, sir.
Yes, you read the second part, this again.
Second one, voltage induced in the second coil if the current changes from 0 to 10 ampere in the first coil in 20 milliseconds.
What it means is, this is time axis. The current increases like this. In 20 millisecond, what happens? The current becomes, this is 0 ampere. This is 10 ampere. So what is di by dt? This time is 10 millisecond, 20 millisecond. Within 20 millisecond, the current changes from 0 to 10 amperes. What is di by dt then, Harinandan?
Sir, di by dt. 10 by 20 into 10 raised to minus 2.
So it is 10 minus 0 divided by 20 into
20
10 power
into
minus
10
3. You should be very
minus 3.
careful about the units.
Yes.
Okay, so how will you do this problem? Two coils. Yes, Harinandan, how will you do this problem?
Sir, we should tabulate the data. N1 is equal to 150. N2 is equal to 200.
Yes.
A is equal to 1.5 into 10 raised to minus 2.
Okay.
And mean length L is equal to 3 meter. And
okay.
mu R is equal to 2000.
Okay.
And the mutual inductance.
What is the formula for mutual inductance?
M is equal to mu 0 N1 N2 A by L. Mu
A by
0,
L. I think so. Mu 0 mu R.
Mu 0 mu R.
Okay, so you should know the formula. Then how will I find the voltage induced in the second coil if the current changes? What is the second? How do you do the second part? V is equal to M di by dt. Let us see the answer quickly.
Okay, sir.
We are running short of time. Yes, I'll stop in 1 minute. I'll share the slides with you. please look, and the group 1 will answer. The answers are there. If you want some additional steps, please write it. And if you have doubt, the group 1 can ask me. Okay. So I'll stop in 2 minutes. Yes. So as Harinandan said, whenever for examination, write all the things very neatly. Okay. Don't scribble up. M is mu0, mu-r, n1, n2, a by l. Everything is given in this question. Only difficulty is di by dt. So di by dt is 10 divided by 20 into 10 raised to minus 3. So you got m. And this is the point. E is equal to m di by dt. So please do this problem, okay, and see whether you're getting. Please look into this question also. This also is easy. So please do these 2 problems. All of you do it on your own. And group 1 and group Harinandan's group, please tell me whether it is clear. Please write it in your own handwriting and send it to me. Okay.
Okay, sir.
You can. I know now Harinandan. I know, and Nandana Rani. I know, and the other student is Deepika, isn't it? 32. 32 Arana Harinandan.
Sorry, 32 or 22.
22. 22 Arana.
22 Deepika.
ദീപിക അറിയാം. 22 നിങ്ങൾ 3 പേരല്ലാത്ത ഒരാളെ കൊണ്ട് ഇത് മൊത്തം നല്ല നീറ്റിൽ എഴുതിയിട്ട് എനിക്ക് അയച്ചു തരാൻ പറയും. Okay. Okay then. Bye bye. Thank you.
Thank you, sir.
See you, God willing, next week in college. Okay. So that will be more fun. Okay. Okay. Bye bye. Thank you.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.